Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So I just had to do some travel for work. And, right now we live someplace where it's like pretty cold. And I went someplace where it was pretty hot. And like packing for that is annoying. So while I was kind of grumbling about the temperature, it got me to thinking, like, what are we actually measuring? Because it probably isn't just like the heatness, but it kind of is, at least in practical terms. But practical terms and scientific terms, they don't always line up so much. So I figured I would ask you, like, what actually is temperature?
Well, darn it, Lions, I am a chemist, not a physicist. But with my very limited knowledge and very limited expertise, I will attempt to opine to this. So first, let's talk about the difference between temperature and heat, because people throw those two things around all willy-nilly like they're the same thing, but they're not. And the difference is very pedantic, and that's what we're into on this show. So, so from your point of view, what is the difference between temperature and heat?
Well, so I think of heat as like, I think we talked about it in our energy conversation, is like heat is one of the like energy radiations, right? So like you can have energy that like radiates as heat. And so I guess I've always just assumed that temperature was just measuring that, right? But I mean, obviously from your context, it sounds like it's not, but also like that seems too reductive to be true because science is just never that friendly to the layperson.
No, science, it's almost like a bunch of people decided to be gatekeepers of science many moons ago, and there's still some of that DNA in our biology. I still remember for gatekeeping, the one that I hated the most was at one point somebody said, "Oh, well, that's potable water." I was like, "Oh, I'm sorry, what does that mean?" And they're like, "Drinkable." I'm like, it's not even shorter. It's just a different, more arcane word. So I didn't know what you were talking about. And then I was just like, hey, sometimes science is dumb, but sometimes it's smart. And so, anyways, temperature is so you're pretty close. Temperature is the measure of the average kinetic energy of the molecules, right? And so that kind of makes sense because all molecules, they vibrate a little bit, and if you pour more energy into them, they vibrate a little bit more, and then they vibrate a little bit more, and then eventually they vibrate so much they start to like move around each other and then kind of disperse into a liquid. And if you keep heating them up, they get real rowdy and they start banging all over the place, and then they go into a gaseous state. So
you should know that I was picturing the molecules in a person until you started to say, then they go into a liquid. And I was like, oh my God.
Oh no. And then the gas, oh no. Yeah. Generally, if you get to the liquid point of the boiling point of a human, things have gone way sideways, way fast. So I say all that to say heat measures instead how energy flows, right? And so the temperature, the unit that we use for temperature is, or the letter that we use for temperature is T. And the letter that we use for heat is Q.
Because why not?
Yeah, because, I mean, H probably had something else. I think H might be entropy or something weird. Something that doesn't start with H, I can tell you that much.
Entropy?
Entropy might be G, I forget. But anyways, I feel like that they were like, oh man, we have 26 possible characters. It's like, but we have 42 or 52 if you count uppercase and lowercase. It's still not enough. Greek letters too. So speaking of, temperature is measured in 4 different modalities, right? Fahrenheit, Celsius, Kelvin, and Rankine. So from your point of view, what is the purpose of all 4? Like, do you know like where all 4 of those come from? Like, how do all those different measurements work?
Well, I as an American, I'm most familiar with freedom units. So we use freedom units to measure temperature. 0 is set at something, and then boiling is a larger number. I think it's 212. So it's not water like Celsius, because Celsius decided to pin to water. I don't actually know what Fahrenheit is pinned to. Maybe nothing. And then Kelvin is like absolute 0, but I think it increments the same way as Celsius. And I don't know that other one.
Sure does. The last one is Kelvin, but for Fahrenheit. So, yeah, no, because freedom units, we were so focused on using freedom units, and then we were like, yeah, but freedom units don't work very well when you're trying to deal with calculations that require you to have an intercept that goes through zero. And then they're like, then we shall create absolute zero freedom units. And it's like, or just another pitch, dump those units and get different units. And it's like, no. Why? Because freedom, son, freedom.
Because freedom units. So let me make sure I understand then. So Kelvin is pegged to absolute zero, meaning no kinetic energy in the system, right? Because you said that's what it's actually measuring is the kinetic energy. So zero there is zero kinetic energy in the system. Celsius then is some amount of kinetic energy, but it's pinned to water. So 0 is freezing, 100 is boiling, and then you have increments in between.
Yep.
What is Fahrenheit pinned to something?
Yes. So Mr. Fahrenheit in 1724 pinned the Fahrenheit 0 to a mixture of ice, water, and ammonium chloride to form an eutectic system. Eutectic meaning that it is allowed to have a lower freezing point than the system as a whole. So in order to get his 0 below the freezing of water, he had to add salts into it to make it so that way 0 was less than the 0 freezing of water. So he had to like work at it.
And this is not something you'd just like find lying around. Right?
Ammonia, no.
Yeah.
No.
So is there some sciencey reason that this would be more desirable than a thing that is like laying around like water or air or something?
So I believe that the system is more stable. But that being said, an ice bath's pretty stable, man, once it hits homeostasis. So, I mean, I really think that this guy was overthinking it. But so that's how he set his 0. Then, in order to draw a line, you need 2 points. And so he said, I shall set my next point at human body temperature, right? And so he set that at 96 degrees. Because this is the Diaries of a Madman. Because it's his scale. He could have pinned it to anything. So he pinned it to this like weird ice bath mixture. He pinned that to 0. I'm like, all right, that's weird, but maybe he had a very specific reason for doing it. It was the early 1700s. People were just throwing science at the wall to see what sticks, right? You know, science was kind of a new concept back then. So, but then to say, okay, I'm now going to pin the other side of it to the human body temperature. It's like, oh, okay, it's cool. So that's 100, right? That would make sense. It's like, no, 96. It's like, but why though? Why? And the only reason I can legitimately think of is to make it deliberately obtuse, you know?
Right. Yeah. Like not hypothetical gatekeeping, but maybe actual literal gatekeeping.
Yeah. Maybe to be like, you see, I am the only one that can make thermometers in Fahrenheit because I'm the only one who has exact access to all of this garbage. So yes. And so then extrapolated out, of course, then 32 degrees is the freezing point of water, as we all know and love, apparently. God, I hate Fahrenheit so much, man. It's so stupid.
You
sorry,
that's just pretty angry.
Yeah, it just, it just makes me think of the SNL skit where it's just like, we'll have one measurement of temperature that the whole world will use and one completely random one. Our nation will use the random one. So those are the units and the unit problems. But then we get into how do we measure temperature? And so now that we have units, we say, okay, so now we need to say what we need to take the average kinetic energy of a thing and put it into numbers that we can then mess around with. So what are some of the different types of thermometers you can think of? And I'm hoping desperately that you only name the 3 that I wrote down.
So you mean like how they take their measurement when you say types?
Well, types. So like, for example, if you were to hold a thermometer, how would you describe that thermometer?
Okay. So like, I guess an old fashioned one would be like a glass with like either mercury or like the little red line in it, little red, whatever, mercury dyed
Mineral
red.
spirits.
I assume it's mercury in food coloring. So there's
oh man, no. So you know how it's not mercury in food coloring is because mercury doesn't adsorb or absorb food coloring. It's not soluble in mercury. Because you want to know something wild is if you take a thing of mercury and you dump food coloring in it, you can then take with a glove on, of course, take a paper towel and sop up the food coloring and just pull it back out of solution because it never gets absorbed by the mercury, which I think is wild, right?
And it is really no wonder people thought mercury was magic. Even once they knew it was poison, it's just like, but it's so cool.
Yeah, no, I mean, like, mercury is completely awesome, right? And so, to your point, right, is that I can definitely imagine people being like, it's magic, and then science was like, no, it's not magic. It's like, oh, still pretty cool though, you know. And so then,
no, keep touching it. Definitely roll it around in your mouth a little bit.
Yeah, right. You know, I mean, like it's definitely good for enemas or, you know, whatever you got going on, you know.
So
yes,
glass thermometer. I guess what you would call a glass thermometer. Then I guess I would think next of like a digital, like a temple thermometer. You know, like if you have like kids or you go to a doctor's office where they like press it against your face and then
digital
it makes
down.
like a little clicky noise, like almost like one of those like laser measuring things. So infrared, maybe. I think they're infrared actually. Like temple tappy ones. And then third one. What didn't we do? Well, I don't know. I can only think of those two. There's glass ones, and then like all the other ones I'm thinking of all use that same kind of principle. They're just in like a different box, like like an air conditioner thing. Like old ones had mercury switches inside, like a thermometer, and then newer ones have some kind of digital thing. So yeah, I got two. I got a 66%.
See, this is fascinating because the way that you've approached this is very much from an IT perspective, right? It's because you're like, well, based off of their readouts, there's analog and digital, and thus there are two, you know? And it's just like, yeah, so you're correct. The digital one actually splits out into two different types, you know? That you wouldn't really know the difference. You would be able to extrapolate the difference, but like you'd have to think about it. So glass thermometers, correct, first and foremost, right? So it assumes homeostasis between the thermometer liquid and the temperature outside of the glass, right? So basically, it assumes that all of that's homeostatic, but it operates under the base principle that what happens when you heat a liquid?
It expands.
It does, right? Except for ice, which contracts a little bit and then starts to expand. So dumb ice, especially ice 9 or ice 3. Hey, we should do an episode on that.
We should have had done that.
So anyway, it's basically so as the water or the mineral spirits within are heated, they expand to, you know, get higher and higher, and then all you have to do is then calibrate that against the actual temperature, and bingo bango, you've got yourself a thermometer. Advantages and disadvantages to this particular type of measurement is one, it gives a direct reading, which means that there's no transducer. There's nothing massaging the data from one domain into another. So it's not like, oh, well, this is in the electrical or the non-electrical domain, and putting it into the electrical domain. Like you stare at that thing and it gives you the temperature, right? So
it's like looking at the markings like on the side of a beaker or a measuring cup. Like That's a direct reading.
Yes, exactly. As opposed to the other ones we're going to talk about where a thing is measured and then something has to massage that into a readout that we can then interpret. Actually, at one point in a class I took at one point, they said, in X system, I think it was, that's what it was, is they said, like, if you were to use a glass beaker or something like that and say that is the system, what would be the sensor and what would be the transducer? And it's like, well, the sensor is the human eyes and the transducer is your brain. And I was like, yeah, but that's not helpful, you know? So,
right. Like, yes, very clever. You wrote a riddle.
Yeah, good job. 2, it's relatively accurate. Number 3, it's cheap, right? I mean, you can go pick up a thermometer for $5, right? This can be a positive or a negative. It is slow to react to temperature changes, right? So it doesn't give you like it doesn't jump around a whole lot for reasons, as we said, is because it has to be at homeostasis with whatever it's measuring. And glass is an insulator, so it specifically does not conduct heat very well. So because of that, it makes it really good for like measuring the temperature outside, because then if all of a sudden, if light strikes the thermometer, it doesn't suddenly go, oh my God, I'm so hot. You know, like it kind of says like, oh no, you know, it gets kind of groovy and it gives you an average.
And the other downside pro is we as older people get to harass our kids and say like, when we were kids, we had your mom, when you didn't want to go to school, had to like sit there with the stupid thermometer under your mouth for so long that she would walk away, and then you would like hold it in your hand and like rub it and like try to heat it up. You can't do that with like a modern temple thermometer. Like if your kids are lying to you about having a fever, you know right away.
Yeah, actually, that's an interesting side note to digress from the prepare topics for a minute. I sometimes think about like all of the shenanigans that we have now scienced out of childhood, right? You know, because like before, for example, you know, if things went sideways at school, your teachers would call your parents, and that's bad. But sometimes your parents both worked, so they'd leave a voicemail on the voicemail. And if you got home first, you could run upstairs and delete that voicemail before they could get at it. And none of that happens anymore. They've got our email. They have a direct line to us, you know. We all have phones on us all the time. So I'm like, oh, man, my kids can't get away with nothing by comparison, you know. And also, too, yeah, is that you can't just, you know, take the thermometer and put it up against the light bulb and watch it get up to like 104. And then your mom comes in and goes, oh, my God, you need to go to the hospital. And you're like, that was too many degrees.
Okay, less than that next time.
And I was sitting here wondering, how high should the temperature be to warrant me staying home from school? And I thought 105 degrees, and that was too many degrees. So also another downside is it has a low operating range, right? So compared to some of the digital thermometers that you're talking about, they have an operating range of hundreds or potentially up to like 1,000 degrees Celsius. These don't do that typically, you know, or at least not well. You know, you can get one that's graduated to a large temperature range, but it tends to lose accuracy at the high end and at the low end. So again, which makes it really, really great for measuring things where you need a continuous reading. Another one is a type of digital thermometer, and it is the one that you did not specifically say, which is a thermocouple or thermoresistor. So,
is that the kind that has a digital readout, but you still got to like put it in your mouth?
Yeah. Still got to touch it the stuff.
Yeah. When you said like, oh, the digital ones fork into two different kinds, I was like, okay, yeah, I was thinking about the screen, not the actual like measuring part of the instrument.
Right. Which again, this is why we need all of these different specialties, right? Because you again, looking from your view, you're looking at like the user interface and like kind of focusing more on that as opposed to the guts of it, right? Which super matters because, you know, if you were like, hey, I need a digital thermometer, a scientist might be like, well, what kind of, and you're like, dude, it doesn't, just something with a digital readout because that's what I need, you know? So this operates on the principle of electrical resistance. So by your estimation, as temperature increases, what do you think happens to electrical resistance?
So as temperature goes up, resistance, at least in like a circuit, would go up.
Yep.
And I'm basing that on an episode of Futurama where Bender is really cold and says, I'm so cold, my processor is operating at peak efficiency because
absolutely
that's yes. And I know like, you know, like I have a gaming PC, you got to keep it cool, but Bender's the one who taught me that.
Oh yeah. Well, absolutely. And actually I did learn recently that there is a limit to that because I left my work computer in my car when it was like, you know, negative 18 degrees Celsius outside. And then I was like, oh, this thing's going to run like gangbusters when I get into work. And it did not run at all. And I was like, oh, there is a limit to how far I can push this apparently. And negative 18 degrees is over that limit. I'm not sure by how much.
Yeah. We had a couple days here that I got into my car and the display, like the clock and stuff, like wouldn't show numbers because the liquid crystals had become ice crystals.
Yeah, that's not what you want. But yeah, so the idea is that electrical resistance of a material increases as temperature goes up, right? So since we have a correlation there, and it is causal, which is very important.
Could you imagine? It was like, well, these two things have nothing to do with each other, but you know, close it up.
Yeah, whatever. I wonder why these digital thermometers always give really weird readings. But yeah, so basically is that there's a resistor in the cell versus a and basically is that as the resistance, it measures the electrical resistance and it's calibrated against that. As the electrical resistance increases, it increases the readout on the temperature. So given a known voltage drop and a known current, you can calculate resistance. Advantages, very accurate, right? Sometimes definitely to the tenths. You can get some that are accurate like out to the hundredths. Like, so it can be very accurate in case, whatever it is that you're measuring a lot of the times in a science experiment where you need to know right now exactly what the temperature is. It has a wide operating range. As I mentioned, like some of them can go up to like 1,000 degrees. I think that we had one time one that went from, I think it was like -200 or something like that, all the way up to 500 degrees Celsius. And that's hot, man.
Yeah.
That's,
and this is using the exact same principle that you would use in like a thermometer you put in a kid's mouth.
Yep, exactly. Yeah, exact same principle, just a little bit more robust design.
Way more robust, I assume.
Yeah, exactly. Although the muffle furnace that I was using to measure the temperature, I found out got higher than 500 degrees Celsius, and I found that out because it melted pieces of the plastic on this digital thermometer. Because I didn't double check before I used it. And then I had to go explain to my boss why I ruined a $500 thermometer because I effectively wasn't literate.
You should know that a muffle furnace absolutely sounds like something you put a stoolie into. Like one of the guys in your gang gets caught talking to the cops and then you put him in the muffle furnace.
Yes. Well, I mean, that would send a message because that's a terrible way to die.
Yeah.
Just for a frame of reference, muffle furnaces, we typically would put in crucibles, which are made out of ceramic, right? And, they would have samples in them. And you would have to label on the outside of the muffle furnace which ceramic containers were which ones, because if you labeled them with ink, the ink would oxidize and evaporate off of the thing. It would burn all of the ink away. And when you're suddenly having to deal with those types of problems, that's a pretty extreme environment. So yeah, don't only put a stoolie in there if you want to send a message, not if you want to get any more information out of them.
Right? Yeah. That is not. I'm going to break your thumbs. That is, you will never talk to the police again.
Yeah, that is. You've pumped the well dry, as dry as their pores will be here in about 15 minutes. Two, it is, finally, it is, as I kind of mentioned, downside is they're expensive, right? They cost way more. And then the final type, which was the type that you mentioned, is the IR thermometer. So it's actually called an IR thermometer, not so much because of the laser on it, but because it measures black body radiation emitted from an object. So
Is that as metal as that sounds? Because it sounds super metal. No,
it's just radiant heat. Yeah. But black body radiation sounds really cool, right?
Yeah. I guarantee you right now in the Netherlands, there is a metal band called Black Body Radiation.
Oh man, that is a good name for a band. So black body radiation, and this is definitely testing the outskirts of my knowledge, is just basically the idea is something that produces heat, and that's basically it. Is if it's used as a source of radiation of heat radiation, it's called black body radiation because the way that they normalize the radiation is that they basically say, we assume that this radiation is being produced from a perfectly black radiant source, so a black body. So it basically measures the thermal electromagnetic radiation surrounding a body, and then it kind of equilibrates that against the environment. So it basically kind of says like, okay, well, I know that the environment is this temperature, so if I poke at this thing, it is giving off this radiation, so therefore the temperature delta would be this, and this is what the temperature is. So
is that if it has to calibrate off the environment, is that why? Because I've seen the thermometer we have for my children is like, you have to press it against the temple and then like drag it across. And then like a doctor's office might have like a more expensive one that you like put in the ear. And then I've seen ones not for people, I don't think, but that you can do from like a foot away. Like, are those all just operating on the same general, like it's calibrating, like it's doing some radiation off of the source and then the environment and comparing them?
I appreciate that was one cogent thought. You said like 5 things we got to talk about. So
so much science in that question.
Yeah, I was just like, well, wait, hang on. No, God, so much. Okay, so in terms of it measuring against the environment, That it just does internally, right? Because it can easily do that through the last method that I said, right? Which is it just has a resistor in there and it measures, what the ambient temperature is. So now I'm going to start taking swags, which I actually found out what swag means recently. And I think that's funny.
This is another place where our two industries have decided on different acronyms, like different words that those acronyms mean. Because for someone who goes to a lot of conferences, swag is stuff we all get.
Yes. And for me, swag means a scientific wild ass guess.
Yours is
oh my God, is that bag full of swag? It's full of scientific guesses. Yes, it is. And it just cuts to me like in the laboratory, and I've got a bunch of like hats and like danglies, like it's just
bunch of lanyards and stickers.
So the reason, my guess, as far as why you need to take the IR thermometer and place it against your child's head and then run it across is because for that one, you need to know you need to know the difference between 100 and 101 degrees, right? So what you don't want to do is one of the big issues with these guns is that they're going to measure whatever you point them at. So they want to remove that source of error. So they're like, put it on the thing you want to measure, not science person, right? And then I'm guessing that they have you run it across there because then it's taking an average of all of the temperatures that it reads. So that way you don't get an inadvertent hot spot on somebody's head that just happens to be warmer. And so that way it'll give you a more accurate reading because it's probably taking like 100 readings across that and then averaging them. For the ear temperature, I think that does a similar thing where it makes sure that you're taking that temperature at that exact spot. And also, too, the temperature fluctuations, the further inside the body you get, the lower the temperature fluctuations. So I guess that thermometer. Yeah. Yeah, right. Think warm thoughts, boy. So I'm guessing that like one that makes sure that you're taking it at the exact same place, and two that the where it's taking the temperature is further inside your body, so it's less likely to run into hot and cold regions. And then the last one that you mentioned, the ones where you pointed a full foot away, those are actually the ones I'm the most used to because we use those in my industry to measure cooler temperature when like coolers show up at the lab.
Right, and I was thinking about it like where have I seen those, and the answer is in construction, right? So like yep. I'm trying to figure out like where there's hot and cold spots in this room. So I'm walking around like pointing this thing at corners and windows and stuff and like trying to figure it out. But there, to your point, like a swing of half a degree or even several degrees is not a problem because what I'm really looking for is a range so big that it is noticeable to the people sitting in this room, right? That spot over there is 15 degrees colder than over here because there's a leak in the window or whatever.
Yeah, absolutely. And so in those situations, because again, what you pointed at absolutely matters. And the distance that you pointed at matters, so like the further away it is, the less accurate the reading. So a lot of times what you'll end up seeing people, because the thermometer will say, point this at the thing exactly this far away. And if you want to see how creative scientists can get, especially on a budget, what we always did was it was like always said like 0.2, either 2 inches or maybe like 10 centimeters, something like that away, is we got tongue depressors and we measured out that distance and we taped it to the bottom of the gun. And then we said, put the tongue depressor on the thing and then pull the trigger. And that worked like gangbusters, right? And people would be like, why do you have tongue depressors on? Right. So it's just like, yeah, like not too bad as far as like we've got this $200 thing that we need to make sure the guy we're paying $12 an hour knows how to use it properly. And it's like, well, get a tongue depressor, tape to the thing. So one, the downside is they are relatively expensive. And two, they are difficult to use properly, as we just mentioned, is that there's a lot of error on them. But three, the nice thing is it doesn't require any real physical contact with the body. Even the one that you're like touching, it's non-invasive, right? As opposed to an actual thermometer, you can't press that against, or a thermocouple, you can't press that against your forehead and get a temperature, right? You need to get it in you somehow. Think warm thoughts, So, so those are some of the ways in which we measure temperature.
You unfortunately have jogged my memory to the suppository joke in Futurama, where it's the giant black pill to help him like breathe underwater. Because I know you mean like sticking a thermometer up there, which would take, I hope, an accurate temperature. But now you've got me thinking about other weird medical stuff, and that is definitely going to lead to some other questions I want to ask you about.